Hello, everyone. Thank you for joining me today. I'm excited to share with you a remarkable transformation story that demonstrates how systematic approaches to configuration management can fundamentally change an organization's delivery capability. Today, we are going to explore best practices for minimizing configuration errors through a detailed case study at DataSphere's CI/CD transformation. This presentation will show you how one company reduced the configuration errors by 87% and cut deployment times by 80%. Whether you are dealing with frequent deployment failures, long release cycles, or constant firefighting, the lessons from this case study will provide you with actionable strategies you can apply in your own organization. Let's dive in. Let me paint a picture of where DataSphere was before their transformation. They were facing what I call a configuration crisis, and many of you might recognize the symptoms in your own organization. First, their error rate was alarming. Approximately 30% of all deployments were impacted by their configuration errors. Think about it for a moment. Nearly one in three deployments failed or experienced significant issues due to configuration problems. This wasn't just causing delays, it was creating a culture of uncertainty around every release. Second, the deployment cycles were painfully slow. Each code commitment took an average of 45 minutes to reach production. In today's fast-paced development environment, 45 minutes might not sound terrible, but when you're trying to deploy multiple times a day, this becomes a significant bottleneck that prevents you from being responsive to customer needs. Third, third, and most critically, their pipeline required numerous manual intervention points. Manual steps don't just slow things down, they increase the likelihood of human error exponentially. When humans are copying configuration values, updating settings manually, or making decisions about what should be deployed where, mistakes are inevitable. This combination of high error rates, slow cycles, and manual processes create a perfect storm of deployment dysfunction. Now, you might be thinking, okay, so deployments are slow and error prone. That's a technical problem. But the impact of configuration errors extends far beyond the engineering team. Let me break down the real business impact DataSphere was experiencing. From a financial perspective, they were hemorrhaging money. Over time, costs were skyrocketing as engineers worked nights and weekends to fix emergency issues. Lost productivity during outages meant that entire teams were sitting idle, unable to work. And perhaps most painfully, they were paying contract penalties for missing SLAs, literally paying money to clients because the systems weren't reliable enough. Client dissatisfaction was becoming a serious concern. Their satisfaction scores were declining, delayed releases were affecting client projects and timelines, and this was starting to impact both retention of existing clients and their ability to win new businesses. When clients cannot trust your delivery capabilities, they start looking at competitors. Team morale was suffering dramatically. Engineers were spending their days firefighting instead of innovating. There was a pervasive culture of quick fixes and accumulating technical debt because no one had time to do things properly. The constant stress of deployment failures was wearing down even the most dedicated team members. Finally, they were facing serious competitive risk. Their slower feature delivery compared to competitors meant they were losing market differentiation. During contract negotiation, prospects were raising concerns about their reliability. In a competitive market, these factors can be existential threats. The message here is clear. Configuration errors are not just technical problems. They are business problems that affect your bottom line, your customers, your team, and your competitive position. So, how did DataSphere address this crisis? They implemented 9 best practices, and we are going to walk through each one. Let's start with the foundation, Infrastructure as a Code or IAC. Infrastructure as a code is a practice of managing and provisioning infrastructure through machine-readable configuration files rather than manual processes. Instead of someone logging into a console and clicking buttons to create servers, you write code that defines exactly what your infrastructure you need. DataSphere chose Terraform as their IAC tool, and it gave them three critical capabilities. First, declarative configuration. With Terraform, they could define all their cloud resources, compute instances, networking, storage, and databases in declarative configuration documents. Declarative means specify what you want, not how to create it. You say, I need a server with these specification, and Terraform figures out how to make that happen. Second, consistency across environments. This was huge for them. They could use the same Terraform configuration with just parameter variation to ensure identical environments. This completely eradicated those work in staging fails in production issues that had been plaguing them. If staging and production are built from the same code, they behave the same way. Third, version control and rollback capabilities. Once your infrastructure is code, you can treat it like any other code. You can review it, test it, version it, and most importantly, roll it back if something goes wrong. This transformation infrastructure from being this mysterious, undocumented thing into something transparent and manageable. The results were dramatic. They achieved an 87% reduction in configuration errors, dropping from 30% to down to just 4%, and infrastructure provisioning became 10 times faster. What used to take hours could now be done in minutes. Infrastructure as code became the foundation that enabled everything else in their transformation. The second best practice was containerization, and DataSphere chose Docker as the containerization platform. Now, why containerization? The fundamental problem they were solving was the classic works on my machine syndrome. You know the situation. A developer builds something on your laptop, it works perfectly, they push it to staging, and suddenly it breaks. Why? Because the environments are different. Different library versions, different operating system configuration, different dependencies. Docker solved this by packaging application with all the dependencies into a single container. The container includes everything the application needs to run, the code, the runtime, the libraries, the system tools. This container then runs identically everywhere on a developer's laptop, in staging, in production. They implemented multi-stage builds to optimize the container images. This is a technique where you separate build-time dependencies from runtime requirements. Your final container only includes what actually needed to run the application, making it smaller, more secure, and faster to deploy. They also established consistent tagging practices using semantic version numbers and git commit hashes. This meant that at any point they could look at a running container and know exactly what code version it was running and which commit it came from. This traceability is invaluable when you are troubleshooting issues. Containerization gave them four key benefits. It eliminated environment discrepancies, simplified dependency management, enabled immutable deployments, which we'll talk about more later, and facilitated accurate version tracking across all their environments. Best practice number three builds directly on the previous two, environmental parity. The problem was clear. Discrepancies between development, staging, and production environment were causing unexpected issues during deployment. Code that worked perfectly in development would fail in production because the environments were configured differently. Their solution was to achieve true environment parity through these three mechanisms. First, using infrastructure as code. They use the same Terraform configuration across all environments, just with parameter variation. Development might have smaller servers than production, but the configuration structure was identical. Second, containerization. They promoted the exact same container images through all environments. The container that ran in development was the same one that ran in staging and eventually production. No rebuilding, no recompiling, the same artifact moving through the pipeline. Third, they use parameter files to separate environment-specific values from the core configuration. Things like database connection strings or API endpoints were parameterized, so the same code could work in any environment with just different parameter files. They implemented automated checks for configuration drift, systems that would alert them if environments started to diverge from their defined state. And they maintained consistent tagging convention so they could always track which versions were deployed where. The visual here is important. Notice how deployment, development, staging, and production also same code commit and database version. This consistency eliminates an entire class of deployment issues. When environments are truly identical except for their scale and specific parameters, you can deploy with confidence knowing that if it worked in staging, it will work in production as well. Best practice 4 addresses a problem many organizations face: inconsistent server configuration. The problem was straightforward. Manual configuration of servers led to inconsistencies, lack of repeatability, and undocumented system states. When humans configure servers manually, even with documentation, variation creep in. One engineer does it slightly differently than another. Documentation gets outdated, you end up with Snowflake servers that are unique but unmaintainable. DataSphere adopted Ansible as the configuration management tool. Ansible ensures consistent and reliable server setup through automation. Let me highlight the four key benefits they realize. First, consistent server configuration. Ansible ensures all servers are configured identically. You define the desired state once, and Ansible makes sure every server matches that state. No more variation, no more, well, this one server was set up differently. Second, repeatable setup processes. They could now automatically provision and configure servers with a single command. Need to spin up a new environment? Run the Ansible playbook. Need to add 10 more servers? Same playbook. Complete consistency every time. Third, documented system state. With configuration as code, they now had a single source of truth for infrastructure state. Anyone could look at the Ansible playbooks and understand exactly how systems were configured. This documentation was always up to date because it was the actual code doing the configuration. Fourth, quick disaster recovery. If a server failed, they could automatically reprovision and reconfigure it in minutes. No more scrambling through documentation or trying to remember how that server was set up. Just run the playbook and you're back up. Configuration management tools transform server management from an art form requiring specialized knowledge into a repeatable, documented, automated process. Best practice number 5 tackles a security and flexibility problem: hard-coded configuration values. Look at the code example on the left. This is what they are doing. Is what they were doing before. Hard coding values directly in application code. The database host port, and username and password are all written directly into the code. This creates multiple problems. When you hard code values, environment specific changes require code changes. Want to use a different database in staging versus production? You need to modify the code, recompile, redeploy. It is inflexible and error prone. There are serious security risks with embedded credentials. That password, secret123, is now in your source code repository, visible to everyone with access. It's in your version history forever. If your repository is ever compromised, those credentials are exposed, and changes are difficult to track. When configuration is scattered throughout the code, you can't easily see what's configured where or audit who changed what and when. The solution, shown in the code on the right, is to externalize configuration using the environment variables. Now, the application reads configuration from the environment at runtime. The same code can run in any environment. You just provide different environment variables. This gave them four key benefits. Flexibility. They could make environment-specific changes without touching code. Security credentials could be stored in secure secret management systems instead of in code. Auditing configuration changes were now tracked and auditable, and version control configuration itself became code that could be versioned and reviewed. This practice of externalizing configuration is fundamental to the 12-factor app methodology and is considered essential for modern cloud-native application. Best practice 6 is all about catching errors early. Automated validation. The core principle here is simple but powerful. Test configuration before deployment. The later you catch an error, the more expensive it is to fix. An error caught during code review costs minutes. An error caught in production costs hours or days and affects customers. DataSphere implemented validation at multiple stages of their pipeline. First, syntax validation. Before even attempting to use a configuration file, they validate that the syntax is correct. Is it valid YAML? Is it valid JSON? This catches basic mistakes immediately. Second, plan review. For infrastructure changes, they use Terraform's plan feature to preview exactly what changes will be made before applying them. This lets them catch issues like, oh, this is going to delete our database before it actually happens. Third, integration test. They test actual deployments in staging environments to validate functionality. They don't just deploy and hope it works. They run automated tests to verify the application behaves correctly with the new configuration. Fourth, health checks. After deployment, they verify application starts correctly and respond to request. If an application can pass its health check, the deployment is automatically rolled back. The outcome of this multi-layer validation process approach is that errors are caught early in the pipeline. Invalid configuration never make it to production, and developers get faster feedback within minutes of submitting a change. They know if it's going to work or not. This shift-led approach to validation, moving tests earlier in development cycle, dramatically reduced the production incidents. Best practice 7 addresses a critical security concern: secrets management. The problem they were facing was that credentials were being stored directly in code or configuration files. This poses serious security risk. Those credentials end up in version control system, visible in commit history, potentially exposed in logs, vulnerable to unauthorized access. And when you need to rotate a credential, say because someone left the company, it becomes a nightmare trying to find and update every place the credential is hard-coded. DataSphere adopted a simple but absolute principle: never store credentials in code or configuration file. Not in comments, not in environments that could get committed to Git, nowhere in your code bases. Instead, they adopted dedicated secret management tools, specifically AWS Secrets Manager and HashiCorp Vault. These are purpose-built systems for storing, accessing, and managing sensitive credentials. This approach gave them four key benefits. First, preventing credential leaks. By keeping sensitive information out of code repositories, they eliminated the risk of accidentally exposing credentials. Second, enabling credential rotation. When credentials are centrally managed, rotating them becomes straightforward. Change it in one place, and all applications get the updated credential. Third, access auditing. They could now track who accessed which secret and when. This audit trail is crucial for security compliance and incident investigation. Fourth, implementing the principle of least privilege. They could control precisely which application and which team members had access to which secrets. The workflow is straightforward. Application code requires credentials from the secret manager at runtime, uses them for the session, but never stores them permanently. The secret manager acts as a single source of truth for all sensitive configuration. They integrated this into their CI/CD pipeline to inject secrets at deployment time rather than baking them into the container images. Now, let's look at the result of implementing all the best practices. The numbers are truly impressive. Deployment time was reduced from 45 minutes to just 9 minutes, an 80% improvement. Think about what this means operationally. If you are deploying 10 times a day, you have just saved 6 hours of waiting time. That's time engineers can spend on building features instead of watching progress bars. Configuration errors dropped from 30% to 4%, an 87% reduction. Going from nearly 1 in 3 deployment failing to 1 in 25 is transformational. This does not just mean fewer failures. It means engineers can deploy with confidence. It means customers experience fewer disruption. It means the on-call engineer can actually sleep at night. But the benefits extended beyond just these headline numbers. Monthly downtime was reduced by 87%. The system became dramatically more reliable. Client satisfaction increased from 4.9 out of 5. When your systems are reliable and you can deliver features quickly, clients notice and appreciate it. And deployments per week increased by 300%. They went from deploying occasionally and nervously to deploying frequently and confidently. This agility allowed them to respond to customer needs faster and iterate on features more quickly. The visual representation here really drives it home. That dramatic drop in deployment time and error rate represents a fundamental transformation in how and the organization operates. This isn't incremental improvement. This is a complete reimagining of what's possible with proper configuration management on automation. These results did not happen overnight and they did not happen by accident. They were the result of systematic implementation of proven best practices which bring us closer to our implementation roadmap. Now, let's talk about what can go wrong. DataSphere encountered all of these pitfalls and learned how to address them. Resistance to change is inevitable. Some team members resisted the new processes. DataSphere addressed this through patient communication and by demonstrating quick wins. They involve skeptics in solution design. When people feel ownership, they become advocates rather than resistors. Knowledge gaps were a significant challenge. The new technology stack introduced learning curves. They mitigated this through organized training programs and mentorship. They created comprehensive documentation so knowledge was not trapped in one person's head. Invest in your team's learning, and they will make your transformation successful. Communication failures led to duplicated work and misalignment. They improved communication channels and established clear documentation standards. They held regular cross-team meetings to ensure everyone stayed aligned. In distributed transformation, you can't over-communicate. Overwhelming data and alert fatigue became problems. They were collecting so much monitoring data that the important signals got lost in noise. They learned to focus on key performance indicators and optimize alert thresholds. They implemented better data visualization tools so humans could actually make sense of the metrics. More data isn't always better. The right data is better. Sequential execution was slowing them down even after automation. They realized that they were automating sequential processes when they could parallelize independent stages. They identified which tasks could run in parallel and restructure their pipeline accordingly. This insight alone cut deployment time significantly. The best practice for avoiding these pitfalls established a culture of continuous learning and improvement. Conduct retrospectives regularly to identify and address these problems early. Maintaining a learning mindset where problems are opportunities for improvements rather than reasons for blame. As we wrap up, let me leave you with four key takeaways that summarize data space transformation. First, embrace automation. Second, achieve consistency. Third, implement validation. And fourth, foster continuous improvement. All of these, look at this visual representation of their journey from 30% configuration error down to 4%, enabled by infrastructure as code, containers, testing, and security practices working together. As the code state, configuration is not just about code, it's about creating reliable systems that deliver value. Thank you for your time today. DataSpace transformation from 30% error rates and 45-minute deployment to 4% errors and 9-minute deployments demonstrate what's possible when you systematically apply configuration management best practices. Whether you are just beginning to your transformation journey or looking to optimize existing processes, these best practices provide a proven roadmap. Start small, learn continuously, and build momentum with early wins.